Rectifying signals is a fundamental part of electronics, due to the many cases where our circuits will be fed by the main AC line. The most common way of rectifying, at least in monophasic cases, is the rectifier bridge. This is an array of 4 diodes in which we can use both semicycles from the AC sine wave, positive and negative, to get a DC output. This is way more efficient than using a single diode to rectify. So here we have the difference between the single diode output and the bridge rectifier output. With a single diode we only have the positive semicycle output, and we are basically losing 50% of the power by not utilizing the negative semicycle. With the case of the bridge rectifier, we are utilizing both semicycles, so by itself we get a twice the frequency output, but we are getting the negative semicycle to turn into a positive semicycle. This is why it's so important to implement a bridge rectifier in this case. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In PrismaSem Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. Now that we comprehend the advantage of using a rectifier bridge, let's go to the analysis. Even though it's okay to use single diodes to form a rectifier bridge, there's an integrated solution in which we have the array inside and ready to work. Why would we use an integrated array instead of single diodes? The first reason is that it's easier to implement. A rectifier bridge simplifies the routing and it's easier to mount. The second reason is that an integrated array is cheaper than buying 4 diodes rated for the same application. And the third reason is that integrated arrays have the option of mounting a heatsink, which will be necessary in many cases due to the power requirements. Well, now that we have seen the most important parameters, it's time to check the datasheet, in this case with the model GVJ2510 from Diodes Incorporated. This is a rectifier bridge of medium power. It has a capacity up to 1000 volts peak and 700 volts RMS. It has a max current of 25 amps and an operating temperature of 100 degrees Celsius, with a transient current of 350 amps, with a duration of 8.3 milliseconds. In our derating graph, we can see the capacity of this bridge. We can see that without a heatsink, we can't surpass the 5 amp limit, while with a heatsink, we can reach the limit of 25 amps. We can understand here that the importance of implementing a heatsink is high. For the thermal characteristics, we have a value of 1 degree Celsius per watt for thermal resistance, which is only for the case of thermal resistance of union to case. The manufacturer makes it clear that the bridge should be used with a heatsink. The operating temperature is up to 150 degrees Celsius. Now let's go to the electrical characteristics. First, we have the diode drop, which is up to 1.05 volts at a current of 12.5 amps. In our graph, we can see that we have a relation between the drop and the current, being less than 1 volt before 8 amps of current. Then we have the inverted current, in which it specifies a value of 10 microamps at a temperature of 25 degrees Celsius and a current of 500 microamps at a value of 125 degrees Celsius. These values are usually standard for this kind of rectifiers. It specifies a total capacitance per element of 85 picofarads. The capacitance will affect the operating frequency. It's not recommended for frequencies above 100 kHz. Well, now that we have analyzed the datasheet parameters, it's time to do some tests in the lab. In this case, we will test the drops between different currents, and the temperature increases between the different loads. So first we have the signal without a load, We only have the transformer and the bridge rectifier, and we have an RMS output of 12.35 volts. So let's test it out with currents. So now we have a load of 232 milliamps, and we get an output of around 12.30 something, which is basically the same as we saw without a load. So we don't see a drop with a small current in this case. So now let's increase the load and see what happens. Now we have twice the load, which is 420 milliamps, and we can see that the RMS is around 11.80 something, which we have a drop of 200 millivolts. Then we can start to see the drop, which will obviously increase with the load. Now let's test out the thermal resistance of the bridge rectifier. We have a room temperature of 21.6 degrees Celsius, and we are operating at a current of 430 milliamps, and we can see that we have an increase of around 10 degrees Celsius. For this case, it maintains averagely the same, so we can expect this rectifier to keep working at this temperature, at this load, for most of the time. It will keep increasing, but by little margins of I don't know, 3 degrees above many hours. Now we have increased the current to 1.4 amps, and we are getting a temperature difference of 30 degrees Celsius. We're starting to see a more significant increase, even though this is not a temperature to be worried about. I mean, 50 degrees Celsius is not a big deal in many cases, but we have to understand that this increase will be above the room temperature. The bigger the room temperature is, the bigger the total temperature will be for the bridge rectifier or any element. And now we have 2 amps of operating current, and we have 70 degrees Celsius of operating temperature. Now we're starting to see why it's important to implement a heatsink for these kind of elements, because obviously the more current we have, the more temperature will be for the diode or the bridge. And we have a relatively low room temperature, so if we have a different type of operation, we will face way more issues with temperature. So in these cases, implement a heatsink, which will be most of the time required, unless the bridge rectifier is very large or the current is not high enough. Well, now that we have seen the analysis, it's time to reach for a conclusion. Rectifier bridges are definitely our allies in the time of designing the power supply for projects. These are simple to implement and a cheap solution at the end of the day. We have to be careful with the values of voltage drop and especially the temperature increase to avoid issues when working with them.